everyone, thanks so much for joining me for this video. Today we're going to be looking at the Boltzmann distribution. So our two learning objectives are to firstly learn about the qualitative explanation of the Boltzmann distribution and its relationship with activation energy, and then to explain using Boltzmann distributions the effect on the proportion of molecules exceeding the activation energy and hence the reaction rate for temperature changes and catalytic behaviour. Now we're going to talk about the Maxwell-Boltzmann curve, and what this distribution tells us is actually how the energy amongst the particles is distributed. So this actually only works for gas particles. So there are four things to note, and the first is that no particles have zero energy. So this area where they have very little energy is very small. So there's not many particles with these kind of low energies. Second thing to note is that most particles have intermediate energies, so around this peak here. So if I drew a line here, then the biggest area is here. So this is where most of the particles are. So most of the particles have these moderate energies. And a very few have very high energies. So again, like the low energies, we have a very few number in this region. And there's actually no upper limit, so this bit here never touches zero. We also need to note that the average energy is not the same as the most probable energy. So the most probable energy is the highest energy that most of the particles have. So it would be about here. And we call this E subscript MP. But the average energy is when you add up all the energies and divide by how many particles there are. So it would be more around here. So this would be the average energy. And also on the distribution, they'll normally put the activation energy required onto it as well. So normally it would be about here, but it varies for different reactions. And the definition of the activation energy is the minimum amount of energy for the particles to require before there's a successful collision. So the area under the graph here, where the particles have either the activation energy or more than that activation energy, is the number of particles which have a successful collision. The Maxwell-Boltzmann distribution curves will look different for different temperatures. So if it originally looks like this, and we have the number of particles, and if it normally looks like this, with the activation energy here, let's say, and then this would be the most probable energy. Well, if we had a higher temperature, then what would happen would be that the particles get more kinetic energy, so more of them have the activation energy required to react successfully. So then we would have a graph that looked like this. So more of these particles here, this area under the graph, would have that energy required, the activation energy required, because that doesn't change. The most probable energy would then be over here. And one thing to note is that, well, the distributions are the same because the number of particles hasn't changed. So if we call this T1 and T2, then T1 is smaller than T2. So these are the temperatures. If we decrease the temperature, it would actually do the opposite thing. So do something like this. So now, in this little area here, even less of the particles have that activation energy required to react successfully, because it's this area under here. Successful particles that collide. So these are the only ones that can actually react. And so this most probable energy is then decreased as well. So lots more of the particles actually don't have the activation energy required. And so we have that T3 is smaller than T1. So now we're going to look at a question, and it tells us to draw the new Maxwell-Boltzmann curves for the altered conditions stated and mark on where the new most probable energies and activation energies lie. So if we start with the first graph, it tells us to increase the temperature. And so we know that if we increase the temperature, then the particles, the molecules, are supplied with more energy. So there are more collisions per unit time, and also the particles, more of them, have the activation energy required for a successful collision. So that means there are more successful collisions per unit time, so the whole rate of reaction increases. So what happens with the graph is that more of them possess the activation energy, and so the graph would look something like this, where this area, because the activation energy hasn't changed, the value of it hasn't changed, and we've just changed this area here, so more of the particles have the activation energy. And also it's important to remember that the two areas underneath the graphs of the normal one and increase in temperature graph are the same because we haven't altered the number of molecules. And so the activation energy has stayed the same, and the most probable energy has now increased to about here. Because the definition of the most probable energy is the highest energy that most of the particles have. Secondly, we're trying to remove half the molecules. So actually, when we remove half the molecules, we don't change anything about how much energy they have. We're just changing the number of molecules. So what happens is that the whole area under the graph just decreases by half. But the whole symmetry of the graph is exactly the same. So it looks something like this. And one thing to note is that the number of molecules with this activation energy is half than what it used to be. And the most probable energy is in the same place. So on to number 3, adding a catalyst. So a catalyst provides an alternative route for the reaction to take place where the activation energy required is lower. And so that means that we decrease this activation energy, so we move it. So maybe to about here. And so there are more particles with the activation energy again, so the reaction rate increases. But nothing changes about the most probable energy, and also the number of molecules doesn't increase. So actually the graph stays exactly the same, and the only thing that changes is that the activation energy moves to a value which is lower. For number 4, we're trying to reduce the volume of the container. So what we do when we reduce the volume of the container is that the number of collisions per unit time increases. But actually, the most probable energy of the particles doesn't increase because we're not supplying them with energy. We're not increasing the temperature or anything. And also, the activation energy isn't changing. So the whole graph is just the same, and the number of particles that possess that activation energy is also the same. For number 5, we're reducing the temperature, so we're doing the opposite to what we did for number 1. So the graph would look something like this. So the whole area under the graph is the same because they're the same number of molecules, but this most probable energy has decreased. But the activation energy has stayed the same. So that means that this area here is smaller than it was before, and that means that less of the particles have that activation energy required to successfully react. And then lastly, for number 6, if we add an inert gas, that means that a gas that doesn't react with any of the reactants, then everything stays the same because nothing's changing about it. We're not giving the particles more energy, we're not increasing the number of molecules. So the number of particles with that activation energy is just the same. And so nothing changes. So for number 2, well, before I get into it, you can feel free to pause the video and try it out for yourself first. So the diagram below shows the Maxwell-Boltzmann distribution of molecular energies in a sample of gas. For A, state which one of X, Y, or Z best represents the mean energy of the molecules. Well, if we look at X, it's not really telling us anything. It's just at a random energy value, so it's not X. And then Z looks to be the average. So when you add up all of the energies, all of the separate energies, all the separate molecules, and divided by how many molecules there were, it looks like the mean energy. So it could be Z, or it could be Y. But Y could also be the most probable energy. And the definition of the most probable energy is so we have the definition of most probable energy, which is the highest energy that most particles have. And so Y looks as though it's more likely to be the most probable energy. So I think for A, the answer is Z, because it looks to be the average of all the energies. And then for B, explain the process that causes some molecules in a sample to have very low energies. So what happens for this Maxwell-Boltzmann distribution to be formed is by loads of molecules being, say, in a box as a sample. So they all collide with each other, and then some of them gain more energy from collisions, but some of them slow down because of collisions. So they'll collide with something, but then kinetic energy will be taken away from them, so they'll slow down. So that's why some of these molecules in the sample have very low energies. So the reason is collisions cause them to slow down. And then for C, what does the area under the curve represent? Now this is a very important point because it's really easy to trip up on what this area actually represents. And the area represents the total number of molecules in the sample. And that's why when we do have an activation energy on the graph, so say here, then this area is the number of molecules possessing that activation energy or more, because the whole area is the total molecules in the sample.